In this video, we will develop shear force and bending moment diagrams for a beam. Consider a 4 meter simply supported beam with 1 meter overhanging span over joint B. 4 kN per meter of uniformly distributed load is applied on the overhanging span. 50 kN of concentrated load is exerted at the tip. On simply supported span, it is loaded with 8 kN per meter of distributed load at the center. The intensity of the load decreases linearly towards both supports. On top of that, 75 kN of concentrated load is acting at 1.5 meter from joint A. Let's check the determinacy of this beam. We know axial force, shear force, and bending moment may develop in a loaded beam. To hold the beam in place, equilibrium must be achieved in x and y directions and moment about any point. Therefore, at least 3 support reactions are needed for every member. For this situation, we have only one beam. 3 reaction forces must be provided by support to make sure the structure is stable. A pin support restrains the beam against in-plane translation. Meanwhile, a roller support restrains the beam against vertical translation. When they are arranged in this way, they can restrain the beam from rotation as well. Moreover, all reactions can be calculated using 3 equilibrium equations. Therefore, we confirm the beam is statically determinate. If we provide too many restraints on the beam, it becomes statically indeterminate. To solve such problem, equilibrium equation alone is not enough. Flexibility method or stiffness method need to be used. Let's get back to our problem. The first thing we need to do is determine all support reactions. By taking moment about joint A, we can form an equilibrium equation contains unknown reaction By. By solving the equation, we know the value of By is 103.1 kN. Next, consider equilibrium in y direction. The sum of vertical reactions must equal to the magnitude of all applied loads. Through calculation, we know Ay is 41.9 kN. Horizontal reaction Ax is 0 because we do not have any lateral load. Next, we proceed to inspect beam internal forces due to these loadings. We split the beam into 4 segments. For these segments, we expect to see different shear force and bending moment functions. For segment 1, we move from left-hand side to right-hand side. The limit of x is between 0 to 1.5 meter, which means the function we obtain later is only valid under this condition. When dealing with varying distributed load, the peak intensity changes with location. Therefore, we need to determine the expression for it, which is usually a function of x. Only then, by taking equilibrium in y direction, we obtain the shear force function. By taking moment about the point x, we determine the bending moment function. For segment 2, the limit of x is from 1.5 to 2 meter. Again, functions of shear force and bending moment are obtained using equilibrium equations. Since both segments 1 and 2 are loaded with varying distributed load, the shear force function is a quadratic function of x. Meanwhile, bending moment is a cubic function of x. This time, we focus on segment 4 and move from right to left. The limit of x is now from 0 to 1 meter. We obtain a linear function for shear force and quadratic function for bending moment. For a subsequent segment, the limit of x becomes 1 to 3 meter. This segment is loaded with multiple types of loading, and the derivation of functions is more complicated than other segments. This time, we have a quadratic function for shear force and cubic function for bending moment. We have now identified all necessary functions to develop shear force and bending moment diagrams. Now, let's calculate the internal forces using these functions. What we are going to do is basically using the right function for the right place. For segment 1, the values of shear force at the beginning and end of segment are 41.9 and 37.4 kN respectively. The bending moment in this segment increases with x and capped at 60.6 kN at the end of segment. In segment 2, shear forces at the beginning and end of segment are negative 37.6 and negative 41.1 kN respectively. For bending moment, it decreases from 60.6 to 41 kN. In segment 4, shear force at the tip of overhanging span is 50 kN. At support B, the shear force increases to 54 kN. 52 kN of hogging moment is developed at this support. For segment 3, shear force at the beginning and end of segments are negative 49.1 and negative 41.1 kN respectively. Bending moment changes from negative 52 to 41 kN. On top of that, we also want to determine the internal forces at every 0.5 meter interval. We need to revisit the internal force functions for segment 1, 3, and 4 to do so. Let's plot these points on respective diagrams. Despite the sign convention, we will plot sagging moment below horizontal axis. Rest assured that there is nothing wrong if you wish to plot it above the horizontal axis. We are doing this for the sake of getting a rough idea on the beam deflection based on the diagram. Then, by joining these points, we have produced shear force and bending moment diagrams for this beam. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.